So hello, everyone. It's a pleasure to introduce today Professor David Spergel, who is the director of the Center for Computational Astrophysics of the Flatiron Institute in New York City. He's also an emeritus professor at Princeton University, where he has worked for 30 years, and is an associate faculty member in both the Department of Physics and Mechanical and Aerospace Engineering. He has been the primary mentor for over 32 graduate students, 35 postdocs, and 60 undergrads, and continues to advise and mentor graduate students at Princeton. David has received a number of prizes and awards for his work, including the Gruber Prize as part of the WMAP team in 2012 and the Breakthrough Prize in 2018. His research interests range from the search for planets around nearby stars to the shape of the universe. He is currently one of the leaders of the Simons Observatory and the co-chair of WFIRST, or the Nancy Grace Roman Space Telescope, which will be the subject of this seminar. Thank you so much, David, for finding the time in your busy schedule and accepting our invitation. You may start when you're ready.
So thank you for inviting me, and thank you for giving me a chance to tell this story. Let me pull up the slide. Good, is that clear?
Yes.
Perfect. So what I want to do today is sort of tell a couple linked stories of the development of what we call WFIRST, but now we've named it the Nancy Grace Roman Space Telescope. Nancy Grace Roman was the first director of astrophysics at NASA, was there when the agency started, was there for many years, played a role as the head of astrophysics in developing missions like COBE that led to the Nobel Prize of developing the Hubble Space Telescope, was one of the pioneers of space astronomy, and NASA, I think, wisely renamed the satellite after her a couple months ago. So you'll see occasionally, since some of my slides are older slides, you can tell when it says WFIRST instead of Nancy Grace Roman. And I'm going to link together the tale of how we got this satellite with the tale of dark energy, and also say a little bit about how we develop science policy in the United States. And that ties into what the next set of missions will be that we'll be developing here. As I mentioned, I'm now at the Flatiron Institute, where I'm director of the Center for Computational Astrophysics. The Flatiron Institute's a fairly new institute. We started 4 years ago. It's funded by the Simons Foundation, and its focus is computational science. So we have 5 centers here looking at computational biology, computational neuroscience, computational quantum materials, computational astrophysics, and computational mathematics. So I want to begin by sort of just setting the background stage. Most of you are familiar with this, but just to give you an introduction to cosmology and the motivations for the project, talk about the US Decadal Survey and how that led to the mission, and then describe how we got to the Roman Space Telescope and talk about its plans in the coming months. So what we've learned in the past 20 years or so is the universe is both remarkably simple and remarkably strange. Remarkably simple in that, in some ways, almost the universe couldn't be simpler. We can describe its basic properties with 5 basic numbers: the universe age, the density of atoms, the density of matter, how lumpy the universe is, and how that lumpiness varies with scale. The laws of physics that we see in the laboratory seem to be valid on the scale of the whole universe, and seem to be valid in time. The laws of physics are invariant, seemingly invariant over space and time. We live in a universe whose total energy is close to 0. Its geometry is flat. Fluctuations are Gaussian. It's about as simple as you can get. But while it's simple, it's also quite strange. Atoms make up only about 5% of the universe. The next roughly 25% is in the form of dark matter, and the rest in dark energy associated with empty space. And we know very little about the nature of dark matter and very little about the nature of dark energy. But what we do know is that they require physics beyond the standard model of particle physics. So it provides strong evidence for there being new physics that we haven't discovered yet, which I think is pretty exciting to realize. In fact, I would argue cosmology with the dark matter problem, the dark energy problem, the need to understand the physics of inflation or whatever alternative theory to inflation would explain the observed large-scale structure and large-scale homogeneity of the universe means that there must be new physics out there. Another piece, which also comes arguably from cosmology, is the fact that we have abundance of baryons over antibaryons, and this baryogenesis problem is another piece of physics that, or observation that suggests evidence for physics beyond the standard model. All right, so we look out in space, and I gave this talk in Chile, I could see, so I haven't edited it. Sorry, it's part of my Latin American tour. We look back in time. The further out we look in space, the further back we go in time. When we are studying the microwave background, for example, we're looking at the universe 13.8 billion years ago. All of what we do rests on the ideas of general relativity, the ideas that we talk about dark matter and dark energy. We're assuming that general relativity is valid on cosmological scales, and so far all the tests we have seem consistent with that. I think a very important test was the simultaneous detection of gravitational waves and light from the merger of two neutron stars with LIGO. That provides important evidence that gravitational waves are moving close to the speed of light and provides severe constraints on any alternative to general relativity. But of course, general relativity really started experimentally, at least, with first observations of light bending around stars. Once we have general relativity, this gives us the expanding universe model of cosmology. In the expanding universe model of cosmology, the way I like to think about this is that we live on the, I suppress one dimension, we live on the surface of the sphere, and that our galaxy is one of many galaxies on the sphere that's expanding out in space and expanding into the future. And the answer I like to give to the question oft asked in popular talks about what are we expanding into is that our universe expands into the future. As we run things back in time, we see the universe collapses not to a single point in space, but to a single point in time where the collapse takes place everywhere at the initial singularity. And one of the big open questions in cosmology is understanding that initial singularity. So a little quick history of our universe. We start out very hot and very dense, growing out of that initial singularity or perhaps a big bounce. As the universe expands, it cools. During the first few minutes, all the light elements form: helium, deuterium, lithium. After about 400,000 years after the Big Bang, the atoms form, at which point the universe becomes transparent to microwave background radiation. When we look at the microwave background, we're looking out back in time, looking at what conditions were in the universe back then. After around 1 billion years or so, galaxies and quasars start to form. When we look at the microwave background, really looking back at that moment when the universe went through its transition from ionized to neutral. And what we learned, back in the first decade of this millennium, back in the 2000s, was that a simple model fit all the data. This is data here from WMAP and then the ground-based experiments at the time, and subsequent data from Planck and experiments like ACT and SPT have only confirmed this basic model of cosmology. And this basic model implies that we don't know what makes up most of the energy of the universe. We don't know why the universe is accelerating. So we know there's something missing. And if we go back a decade ago, when we started the last decadal survey, one of the things I was involved with in that process is just talking about what are the big questions in cosmology. And at the time, and I would argue still, it's not a very hard question or challenge to answer. It's easy to come back with this list of questions. I think most of us would agree are the key driving questions: what's the dark matter? What's the dark energy? How did the universe begin? And this became the focus of what we wanted to do when we went to prioritize what the next big mission should be. So in the US, what we do every decade is the National Academy of Sciences organizes a community effort to identify the highest science priorities. And we actually do this in different fields. So I'm going to be talking about the astronomy decadal, but we actually have a very similar process in planetary science, where our planetary science colleagues prioritize whether the next big missions ought to be to Mars, to Jupiter, to Saturn, where ought they go. There's a similar process in heliophysics and in earth science from space. And this is spread from the space sciences to other fields. So our colleagues, say in ocean sciences or polar sciences, also identify what they feel are the top priorities in their field. And what has generally been true is, and this has actually had bipartisan support and generally persisted through even the Trump administration, which has not been noted for its support of science, is that they have looked to the national academies for identifying what the top science priorities are. And Congress has supported this, the bureaucracy has supported this. So what is recommended in these decadal surveys tends to be what gets built. So the things what we looked at, and we're now actually in the midst of this process again for the 2020s, the 2020 decadal survey is now actually in closed sessions, figuring out what the priorities are. The process begins in many ways with white papers from the community identifying the top science questions and ways to address it. Then there are science panels that identify what the top science priorities are. In the 2010 survey, I chaired the cosmology panel, so as part of that, the science panels, after identifying the top questions, we then turn to the prioritization panels. Still in the process of chairing a panel on what we call enabling foundations, which is everything that's not a big mission for this decadal survey. We have an independent costing process and then issue recommendations. And when we make these, do these surveys, we send the recommendations to a number of customers, as it were, the government agencies, Congress, our what's called the Office of Management and Budget, which plays the role of the Ministry of Finance, or in many countries that actually sets the federal budget. It's also read by universities, philanthropists. And I've actually encouraged our students to look at it as a way to get a sense of where the field is likely to go. So in the 2010 decadal, the top priorities in space, or sorry, the ground first was LSST, now called the Rubin Telescope. And DOE and NSF took up this instruction, and they've been building the Rubin Telescope, which should see first light soon, and to be studying dark energy, studying the variable universe, and really do a broad range of things. I'm going to focus on what was the top recommendation in space. The WFIRST mission, it's now called Roman, and so I'll talk about its role. And then it recommended various mid-scale programs in fields like CMB. The recommendation was to wait for Planck results before the next step, and other things. For those of us who also work in CMB are eager to see is what was recommended in the 2020s for CMB work. So actually, before I turn to what the Roman instrument looks like, let me actually now tell the story of how we got from the decadal survey to the mission we have today. When the decadal survey was written, the goal was to be able to build something that was fairly safe. We were pretty comfortable we can build, given the difficulties in developing the James Webb Space Telescope, which actually has taken up much of the subsequent decade after we have not yet launched it, even though it was recommended back in the 2000 survey. The survey recommended building a 1.6 meter telescope with just imaging capabilities. Unbeknownst to us when we were developing the Decadal survey, the National Reconnaissance Organization, this is the part of the US government that builds spy satellites, had been building and developing spy satellites for, well, over 30 years, 40 years before this. The Hubble telescope is basically the spy satellite of its time, KH-11, converted into an astrophysics instrument. And the National Reconnaissance Organization has launched something like 16, 17 Hubble-class telescopes over the past 40 years. And those have been all designed to point down and image the Earth. And you can estimate their capabilities fairly easily by asking, what can you observe from low Earth orbit with a telescope the size of Hubble? And back in the 2000s, there was a program to develop the next generation spy telescope. This program ran into a bunch of technical problems and got canceled. But what it left behind were two optical telescope assemblies, two complete 2.4 meter telescopes with the, so Hubble-sized telescopes, but with more than 100 times the field of view. And these telescopes were going to be destroyed because the program was canceled. But people at the company that developed them felt that these were, terrific optical systems, and that it was a waste to destroy them, and that there was an opportunity to turn this over to NASA. So I was chair of the National Academy's Astrophysics Committee. So I was contacted by John Grunsfeld, who was then head of science at NASA. And John told me, we just got two 2.4 meter telescopes. Do you think we can use them for WFIRST? We can't make this public yet, but we'd like you to lead a very small informal study to look what we can do. And this was an incredibly exciting opportunity to be given in a telescope with really twice the collecting area of what we planned for WFIRST, and to think about what uses it might have. We came up with an idea to not only have a wide field instrument that evolved into the one we have today, but to also add a coronagraph. And that this would be an opportunity to have a place that could develop the technologies needed to image Earth-like planets. This is something that we've been eager to do for a very long time, but it's very hard. Well, we were sort of at a catch-22. We could not build a small telescope with a coronagraph as a test facility, because no one wanted to spend $1 billion on a test facility. Nor could we embark on a major new mission that would use a coronagraph to image planets, because no one wanted to build the next telescope after James Webb, whose core science relied on technology that's never been tested. So having this bigger telescope was giving us an opportunity to develop and test a coronagraph as a technology demonstration instrument that can show that coronagraphs can work in space, can teach us how to use them, and that's worked out very well. So we reported back to NASA that we thought we could do this after first internal politics, and then a number of trips that I've taken over the past 7-8 years to Washington, D.C. to talk to congressional staff about the opportunities here. We convinced them to go forward and build this, and this evolved into what is now the Roman telescope. Scientifically, this telescope really rests on 4 core science cases. We have a telescope with 100 times the field of view of the Hubble telescope. And that means you take every Hubble image you've ever seen, make it 100 times bigger. You can now carry out a program because it's actually can image faster and more efficiently because it's going to be sitting at L2 rather than at low Earth orbit. You can image Andromeda, do the FAT program that Julianne Delcanton led, with that whole program with 2 pointings rather than 400 pointings. So depending on your program, you are 100 to 1,000 times more efficient at imaging the sky. So there's really a wealth of things we can do with that. In fact, I think we are likely, certainly, to survey the LSST footprint in the infrared, and probably eventually over the lifetime of the mission, we will survey the entire sky at Hubble resolution. A big part of the program will be to study the dark universe, as I talked about earlier in the talk. One of the great questions driving cosmology, certainly, and perhaps all of physics, is understanding the nature of dark matter and dark energy. We will carry out an imaging program that will do an exoplanet census by looking for the effects of planets through gravitational microlensing. So the telescope, with its large field of view, will stare towards the galactic center for a couple months a year, image a few square degrees towards the galactic center. We expect to see large numbers of microlensing events, and some of those will have little blips on top of that stellar lensing event due to the presence of exoplanets. As this figure below shows down here, so you can see this one in the lower left corner, you can see the range of planet radius, mass and radius covered by Kepler, and what will be covered by the Roman telescope. And you can see why Kepler and TESS are very good at detecting and studying planetary systems with planets inside the radius of the Earth. That WFIRST will be very good at studying planets like Jupiter, Saturn, Uranus, in fact, planets with masses down to that of some of the asteroids, and really characterize the outer part of systems and really complete the exoplanet census. And as I've already mentioned, there's a coronagraph on board that will let us make steps towards imaging Earth-like planets around other stars. So I think of this as addressing some of the key questions that were brought up at the last Nobel Prize lectures. I had the pleasure of taking a trip to Sweden last December, where I saw Jim Peebles and Didier Queloz Mayor share the Nobel Prize. In his Nobel Prize lecture, Peebles talked about the big questions that lie ahead, being what is dark matter, what is dark energy, how do the structures evolve to make the galaxies we see, how did the universe begin, what's its fate. Those are the cosmology questions that the Roman telescope will address. And as Didier noted, talking about what we know about exoplanets, the big questions there, what explains the diversity of planetary systems, what are the properties of exoplanets, and ultimately, do they host life, are the questions that we hope to make progress on as well. So we were hoping to address some of the major questions this way. So more about the telescope itself and how it will operate. We will have a very large wide field infrared camera. We will have filters ranging from the red, or arguably the orange, sort of around 55,000 angstroms, out to, we will now have a K-short filter that will go out to about 2.4 microns, and will be capable of imaging the sky at, with all those different filters. You can see that the camera is much larger than the cameras on Hubble or JWST, and really will let us carry out a program of wide field imaging. That will let us address a lot of questions in the nature of dark energy. We can use this camera to see supernova out to redshift 1.5 to 2, use them as standard candles for probing the relationship between distance and redshift, carry out a program of weak lensing, and also through doing spectroscopy with H-alpha and oxygen-3, measure large-scale structure, use that to get EAO distances, look at redshift space distortions, and combine all these together for precise measurements. And, you know, going to the infrared will be a very nice complement to, for example, the work that Ruben will do in the optical. One of the things I think we are very likely to do is cover the entire Ruben footprint in the infrared with a wide band over the first couple years of the lifetime of the mission. And it's going to be, compared to the other things that will be available going at the time, going much deeper in the sky. You can see the comparison with the European Euclid mission, which will do terrific things, but will really be probing a closer portion of the universe when it does things like spectroscopic surveys. And this compares the sort of density of what Roman is likely to achieve versus Euclid. For the weak lensing work, the baseline survey we're looking at covers about 2,400 square degrees, will involve measuring shapes of about 400 million galaxies, and let us make 1/10% precision measurements of a matter clustering through cosmic shear, and really have high density maps. In designing the mission and its operation, our focus has been not on maximizing the statistic or minimizing the statistical errors, but actually minimizing the systematic errors. I think we have found for most measurements that we do, where we want to do some precision work, we are limited ultimately by systematics rather than by statistics. So the baseline plan is to actually measure shapes in 3 separate filters with a total of 6 different passes over the sky, and have lots of ways of doing internal calibration of the project. And we'll have, with a telescope of this size, a small and very stable PSF. We're at the L2 Lagrange point, which is a very stable point in terms of a thermal environment and a dynamical environment. And this gives you a sense of the depth we hope to achieve with the high latitude survey. In the blue is what we'll achieve with 10 years of LSST, 10 years of the Rubin Observatory, and in the red, what we'll achieve in 10 years of WFIRST. And the numbers you see are the PSF half-light radius in milliarc seconds. So you can see that the galaxies that will be imaged by the Rubin telescope with sort of 400 milliarc second resolution will have about 3 times better resolution in the infrared. And by combining these, we'll have this 9-band, potentially if we use K-band, 10-band image of all the galaxies across the sky. And it'll be, much deeper than what we will initially get from Euclid when it launches in 2023. Euclid will actually be very nicely matched to the first-year Rubin data. So I think we'll see a situation where we'll start with Rubin cross Euclid in the mid-2020s and look forward to the WFIRST cross Rubin data when as we move to the late 2020s. Here's some numbers showing wavelength coverage and sensitivities and things like that. And people want that. There's a long paper, a pair of long papers that were the reports by the team working on developing WFIRST that I helped put out that are available for people who want real details on the capability of the project. And while these were put out already now, 5 and 3 years ago, the project has pretty much stuck to the reference numbers that we have in that paper. We're now in construction and I think likely to achieve the capabilities that we hope for in the design phase. That design reference mission is one potential way we have of using the telescope. We use that to set the requirements. For example, for the high latitude survey, we assumed that we would do a multi-band study of a couple thousand square degrees. Recently, we've been exploring other possibilities. This is a paper that Tim Eifler led that looked at the idea of what if we take the WFIRST mission, take its widest span, and survey the LSST footprint. And by using such a wide band, we can survey the entire footprint at the needed depth in only 5 months. And what Tim and collaborators, and I was part of this effort, showed is that we could actually achieve a figure of merit, our ability to constrain dark energy parameters, that was more than double that of LSST after 10 years of operations by just adding 5 months of WFIRST data. And this would also provide, which has a tremendous amount of applications in astrophysics, combined, we would have Hubble quality imaging in the infrared across the entire LSST footprint. So we're hopeful that we will add this as part of the program. The observing program of WFIRST has not yet been determined. NASA is going to announce a competition and a process to do this in the next few months. It will be open to the world community. I should also mention that the data from WFIRST, there'll be no proprietary period. So as we take the data, we will be making it available as soon as possible to the world community to access. And one of the things I'm actually most excited about is thinking about the synergies between Roman and the Rubin telescope. Here are a picture taken about a decade ago of Vera Rubin on the left, Nancy Grace Roman on the right, two of the real pioneering figures of 20th century astronomy. They're part of their legacies are these two telescopes, and this rich combined data set, I think, will yield a host of astrophysics from stellar work to cosmology. In cosmology, I think another very important way we'll use this telescope, and this is something we are likely to select these fields in the next coming year, is we're going to identify some fields that we will be using for an ultra deep survey, probably something where we'll take a single field covered by the camera, which is about a little bit more than a quarter square degree, image in all the bands, get down to about 29.5 to 30th magnitude AB. With this in the ultra deep field, we anticipate seeing, and you can look at this plot on the right, well, the axes didn't reproduce very well, but I have the numbers here on the left. Tens of galaxies at redshift greater than 15, hundreds at redshift greater than 12, thousands at redshift greater than 10. These will all be superb targets for follow-up observations by the James Webb Space Telescope and the next generation of 30-meter telescopes. So getting from this mission off the ground has been a long path. In some ways, it started in the 1990s when Saul Perlmutter proposed a SNAP mission. About the same time, I was part of a group that held some workshops talking about designing a telescope to survey the sky in the infrared to complement the optical surveys. In the late 2000s, we had the Joint Dark Energy Mission studies that sort of didn't lead to anything but immediately, but did feed into the Decadal survey. I've already talked about the process by which we learned of that. We held this conference in Princeton in 2013 and started the Phase A studies. We have the distinction of actually having both the Obama and Trump administrations try to cancel the project, mostly because of a lot of resistance to starting anything new in OMB. But we have survived with the support of the community and lots of hard work. And the project is now moving forward. Right now, the mission has passed the what NASA calls KDP-C, which means it's now entering construction phase. What this means really now is that we've already spent over $1 billion. There's $2 billion left to spend in this coming, some of it actually about $500 million in this coming year, is right now in the peak of construction. While the president did zero in his budget for 2021, the Senate actually yesterday just overrode that and fully funded it. So we anticipate being fully funded in 2021. While we don't know what the NASA policy will be like in the Biden administration, they have just announced actually yesterday the transition team. And I think we will have a transition team that is much more supportive of science in general and certainly supportive of astrophysics. Right now, we're on schedule for a launch in late 2025. Even with COVID, we have still not slipped from our November 2025 launch date because the elements right along the critical path have been moving forward. However, there are a lot of delays in the supply system due to COVID, and I would not bet good money on a late 2025 launch. I suspect we will be launching sometime in 26. So let me leave you with this discussion, with this image of what we're doing, which is we're going to, for astronomy, which is we'll really be able to image the sky at Hubble resolution, but with 100 times the field of view. And Hubble's been wonderful, and I think 100 times Hubble will be even more impressive. So I think this will be something that will provide significant opportunity for the scientific community. It will be available to really all. So let me encourage you to think about how this will affect your science and think about ways we can use it most effectively to advance astrophysics. So let me stop here. Thank you.
Thank you very much, David. For the people following us on YouTube, please post your questions there and we'll get to them later. And now